Hi everyone, welcome to the series on sequence model for the text data. In this video, we will see how the RNN works in terms of the hidden state. In the previous video, we saw how the RNN takes the input at each of the time step and computes the activation at the hidden layer and then subsequently calculates the output for each of the or at each of the time step. Just to do a big brief recap, so the input provided at time step 0 to the RNN cell. Now this RNN cell is characterized by number of cells in that particular unit, and that defines the memory of the network. So the input is going to be multiplied with the weights matrix, and then the activation initialized with a value of 0 and produces the activation at the time step 1. For this particular time step, we use the another weights matrix, which is multiplied with the hidden activation at this particular time period, and then the output is derived from that. So the activation at the time step 1 follows this linear transformation, which is essentially the multiplication of the input. So let me just help you with that. So this input is the embedding, and this one is your weights matrix, which connects the data to the activation layer. So this one is that particular weight matrix, and the activation which is produced here or previous activation is taken in here and multiplied by the weights matrix again. So this weights matrix here, WAA, connects the another layer here. So that gives you the activation at that particular time step. And similarly, we calculate the output based on the activation that we achieved, multiplied by the weights matrix again, and added by the bias term. The activation function used in the output is typically softmax most of the time, but for some applications like classification and sentiment analysis, you might want to use sigmoid. Tanh and ReLU are used in the hidden layers, and exactly the same replica of the computational process follows in each of the subsequent time step. So let's see how the computation of the hidden state is done in the RNN. We will see how data is first set up for RNN. We'll go through the forward propagation process, and then we compute the hidden state at each of the time step. This is an arbitrary RNN network with 5 time steps, and each of the time step is going to take the input here. So this is the input taken by the time step 1, 2, 3, 4, 5. So let's see how the computations take place. We'll use dummy NumPy data here. For reproducibility, just use some seed. And just a second, there's an error. Okay, so the data, I'm going to create a dummy data, let's say, 10 samples. The first we will generate the tokens of the word, and each of the word will be assigned with 2-dimension embeddings. That's randomly generated by using random package of NumPy. Let's associate the words with the embedding that we generated in the previous step. And that's how the embeddings are now, associated with the tokens. Now, from those tokens of word or list of tokens, we are going to generate sample sentences, 10 of them, and each sentence will comprise of 2 words from the token list. So you notice here, this is one sample, and the sample is represented by the input vector in terms of embedding. So this represents your intelligence, and neural is represented by the embedding vector, which follows after this. Now, if you combine all of these samples, it becomes a batch of samples, and essentially that converts into a three-dimensional vector. So essentially what we did is, here, let's say this is a time step for a particular time step, and we have embedding E1, E2, and E3. Similarly, the next time step, again, E1, E2, and E3. So this is word 1 and word 2, so on and so forth. And all of these words will define one particular sample. So this is one sample here. And then, so this is a sample 1, and exactly the same replica will happen for sample 2, and put them in all of the samples in a batch. So that gives you a three-dimension array. And this is the basic method that we use to set up the data in case of sequence model. And more specifically for RNN and LSTM, we will follow this particular method. So that was a discussion on how we set up data for RNN. Let's take some random sample of two words. This is word 1 and word 2, essentially two time steps. And we'll go through the process of, um, you know, how the RNN computes the hidden state. So let's make an assumption input dimension is 2, output dimension is also 2. It could be any number depending on your use case. Memory vector again can be configured to any size. In this particular example, we'll take it 7. And that's how you initiate the memory vector. First weights matrix, which connects the input, and the hidden layer is WAX here, and that is bound to the input dimension and also the dimension of the hidden layers. So mention those and generate the random initialized value for the weights matrix. Similarly, the bias term which connects the hidden one, and there are 7 units, so we're going to generate those 7 arbitrary numbers to start with. Hidden to hidden, 7 units to the next 7 units, that would be 7 cross 7. That would be arbitrarily also created. At the output, we are connecting the hidden activation to the output. So again, the specifications have to match with the hidden and the output dimension. So we kept the output dimension as 2, so that's why you get these two numbers. And the bias term is also connected or connecting to the output, which is 2 dimension. So let's generate again randomly the bias vector. This is the bias vector. Now you have all the weights with you. We just need to make one pass, forward pass through the RNN. And these are just simply the placeholders for saving the computation, and later you can verify. Time step 1, this is the linear transformation that happens to get the activation or hidden state. And this is simply tanh. It can be value also. And this is exactly the same formula that I'm showing you up here. So this generates the hidden state, and the hidden state is represented by 7 units because that's the size of the memory or context vector. Right now, the hidden states, all hidden states is having only one because we haven't gone through all the time steps. So this is showing you exactly the same value which you got in the time step 1. And the output, again, the same similar linear transformation, the weights which connects the activation with the output and the activation itself plus the bias term. Just simply follow that equation and it's going to return you a linear transformation in terms of logit, and that goes through a sigmoid or softmax activation. Now the process is the same for next time step. Take a look at the time step 2, and which is exactly the same as time step 1. So only difference is in time step 2, we will be utilizing the hidden state from time step 1. So in this particular video, we saw how we calculate the hidden state, namely the activations in the hidden layer, and we saw how we compute the output at the output layer. Now, what are the use cases of these two? We will see in this subsequent lecture. And in the next video, I will show you how to obtain these values by using Keras. See you in the next video. Thank you all.